focus on the screen, right? Here is just a little video of molecular dynamics that you have recently practiced, right? And one of the presentation subjects will be teach everyone who didn't get it how to make it. And one of the assignments for the whole will be to make things like that, publish on YouTube and send it a link. Oh. So, and without VMD it is possible, but very hard. So with VMD it is so much easier. So we are approaching the Kohn-Sham algorithm, but actually it's not Kohn-Sham algorithm what we will be chatting today. It will be more like Kohn-Sham universe. We are going over density function, and it is a tool to compute total energy, and then later dynamics, orbitals, things like that, right? So it does all things that Hartree-Fock is doing, but more from different principles and sometimes quicker. We covered theorems that are on the background of density functional theory, but now we need to make a bridge to practical calculations. And you do know from the previous classes, previous meetings in this class, that density defines everything, and if you know correct density, you will be, in principle, able to find minimal energy of the system, total energy, right? But there were no mentioning of how to get this total energy. What is the computational procedure? And we are looking forward for a couple of meetings on to cover this procedure and what is actually being done in the software. So today is Thursday, something like 28th of March. Like next Tuesday will be like April 2nd. When I will announce by email, it will be either substitution by a grad student or skip lecture. Next Wednesday, April 3rd, there will be lab for sure, substituted by either a grad student or postdoc, because there is an important material to cover. And on April 4th, I will be back for next lecture with guarantee. And a week from that, 4, 7, it's too hard for me, 11, right? Yeah. So April 11, it will be presentations. In the class, there are a total of 4 presentations. Last one will be presenting results of the in your projects, and number 3 will be WASP skills. So it is the form that you are feeling right now.
Dr. Dimitri?
Yes?
Like the recording device is not here because Daniel took it out earlier. So I'm going to go to his office and grab it now.
Okay.
So I'm going to be back in like 5 minutes.
Oh, sure, sure. Please do, please do.
I have a question.
Please do.
So for the final presentations are in May, right?
If we would not have conferences and snow, I would try to do final presentations before finals week, but maybe because of all delays, it will be due on the finals week.
Okay, okay. And we're presenting in the Department of Chemistry?
You're presenting in class, but there will be guests. It will be a public event.
I got a little scared because I thought we were presenting to the entire Department of Chemistry, so I got a little confused.
No.
Okay.
No one prevents all Department of Chemistry to come here, but highly likely maybe 5%, like one more faculty will join, or maybe 2 more faculty will join.
I don't know. We're pretty cool people, though. They might want to.
Okay. So, please, maybe you have already selected, but if you didn't, you can. VASP input, all things are challenging. I don't know if it is in principle possible to present in 3 minutes, but please try. So, how to convert other formats that you are aware of into VASP format, how to analyze VASP output and make density of states. I will not cover projected density of states, but you may try it on your own or ask Dr. Yoon Han, who will be likely substituting the lab. Scripts, the word scripts is not quite right. The batch scripts for submitting jobs. So overview practical ways of running VASP jobs. Like if you are on the Quarry or Edison, you can submit SQ as batch and then different scripts for submission. You may look inside and check how to change it, how to optimize optimize not geometry, but how to optimize your computational effort, right? It is what to submit on 1 node or 20 nodes, how to number of cores. So to make sure that things go quickly. Of course, you can mention this backup way on the photon, and if you have access on Thunder, you can cover how to do VASP there. But Quarry and Edison are primary targets. Orbitals, it is what we did last night, and everyone practiced how to do it with Gauss view, and I know that Sudipta already did it with VMD. So at least we have one backup expert in the class who already know the skill, how to plot orbitals with VMD, and you can certify that it is not too hard.
No, it's not hard.
Momentum dispersion, completely new material that I rely on my helper to show on the coming Wednesday. So it is how energies of HOMO and LUMA depend on the value of momentum. And it's more important for like people who deal with periodic solid state semiconductors or metals, but for all of us we need a little flavor of this thing. Anions, cations, excitations. This will be also covered next lab, and this is a simple thing analogous to changing spin and multiplicity in Gaussian and looking for consequences. Spin polarized dose, it's basically how to make density of states if you changed the oxidation or multiplicity of your model. The set of scripts follows the same idea, but there are just a couple of keywords are different. And it's not hard, but one needs to practice and present. UV visible spectra is your favorite subject that you all have successfully completed in the submitted homework, and graded homework, right? Okay. And this is how to do the same spin polarized absorption. How to compute spectra if you change spin multiplicity. Also, there are little practical changes, but it's not hard. Thermal heating, what we did last time. Naturalistic bend I will not cover, but again, you may ask helper next time. If you do not find and do not know how to do it, you can skip it, but it is an analog of transition state searching in Gaussian. There is a way to do it in VASP. Okay, and I already have a volunteer for, if I would be in the class, I would select number 11. It's my favorite, making movies. So by now, we already have volunteers for everything except spin polarized absorption.
I'll take it.
Well, you are already signed up by your colleague for naturalistic bend, but okay, thank you. I'll write as a second choice.
Naturalistic.
Second choice.
Sign me up for whatever's left.
Oh, okay. So, Kevin, you have momentum dispersion. As a physics major, you may like it. Anions, cations, or if you want to fight with Mary about spin polarized stuff.
I'll do momentum dispersion.
Okay.
I'll do the spin polarized DOS. Wait, which one am I doing? Number 6 or number 7 or number 9?
Queenie placed you to number 10.
Oh, that's fine.
And who is not signed up? Who is not in the
Me
club?
and then us.
Okay.
So
Then we will
they
give
can
them.
give them, yeah.
Okay. Well, anions, cations is rather easy. Spin polarized absorption, not okay. We will discuss with them. Well, there is no recording anyway, and it's probably not a good resolution, but I'll probably scan later and distribute. Yeah, it's the same thing, just. So, before recording facility is coming, I'll just entertain you a little. So, right now, your main focus is presentations. The second focus is to start thinking creatively on your research projects. Mini, like not overall, but mini research projects for the course. Since you already know skills on molecular dynamics, you are now equipped to start designing your project, if you haven't yet. Next time, next week, you will just get additional skill how to model anions and cations, which is important. Like if you ionize system, they change their reactivity and electronic properties, like all characteristics, but it's not super much. I'm giving just a list of possible projects that were considered for previous years or successfully done in several previous years. So you do not need to literally follow, it's just ideas. Like maybe from childhood you wanted to make a lightsaber or laser gun for Star Wars, and therefore you want ruby laser to model, which is like chromium doping into aluminum oxide. Maybe you want to fly to the moon and you need rocket fuels, right? Or you are attached to perovskites in one of the or other forms. So
what is the SiO2 pores about? I already have a topic, but for those that are undecided, that sounds interesting. That number 6.
I know the answer. I just focusing the right words. The silica itself is a crystal, is a like sand, glass, right? And there are chemical ways. I don't know if it is interesting for everyone. Maybe it's boring. Chemical ways of fabricating silicon dioxide from a molecule, precursor molecule that exists on one silicon atom, and then long organic chains to the 4 sides.
Okay.
The abbreviation is TEOS.
Okay.
TEOS. And then when you process the precursor, it grows like a quantum dot. But if you start growing this silica in the environment of micelle polymers, like little balls, it will grow around them. And after you grow it, you can bake it in the oven. Polymers will burn out, and it will create like a little sponge made out of silicon dioxide. And then it has like for catalytic or gas purification. Just for your curiosity.
Queenie, that might be a topic you might want to pick. That's a good one for the polymer side, if you're curious.
Oh, thank you.
It's a hot one.
Good.
Just FYI.
A person who did this project in the past later wrote a paper in the it's not super high impact journal. It's like catalysts, like impact journal 3.5, and it was awarded as the best paper of the year.
Oh, okay, Queenie, you got your work cut out for you.
So other,
Thank you.
well, you still can redecide, but no pressure and no rush. You still have time. One of the projects that is, it's already taken. There is a last year undergraduate who took this course previous year who is actively pursuing it, like perovskite slab connected with electron acceptor with titanium dioxide and Hall acceptor, which is like another shape of another type of a molecule. So it's one can look into like catalysis by metal organic complexes or by charge transfer between semiconductors, substrate, and metal cluster immersed in water. This project was originally considered last year, but then, so it is like toxic activity of oxides onto cell membrane. But later on, to have it running quicker, the toxic surface of metal oxide was replaced by hydrogen peroxide, which is a little easier to compute, and it was degrading this material like crazy. But these bio-related things are possible to do. Ready to start?
It should take like a few minutes to start,
Okay.
but if you try recording, let's see if we can do that.
So in worst case scenario, this meeting will be not recorded, but then we will watch, those who need can watch the recordings from previous years. Interface between silicon and silver nanoparticles. And here is the biography of Walter Kohn, who actually got a Nobel Prize for designing density function theory together with Popov. Well, right now he is not with us anymore, but he was living long life, and right after his departure on the Sunnyvale conference, there was a special session in his memory, and one of his former graduate students, Kieran Burke, actually we all are running PBE functional, which stands for first letters of the last names of the people who designed. PBE is for Purdue, Burke, Erzerhoff. Letter B in this PBE function, Burke was telling a story about how he was. He's originally from Irish, and he was assigned to give a seminar in the group of Walter Kohn, and he was fearing because he was not prepared. And he decided, came to the room, and he just was full of shame being not prepared. And then thought like, wait, I need to run to my room for my notes. And while departing for the notes, he decided like, probably I will never return back, just buy ticket to back to home and quit the program. But then on the way he remembered that in the research group of Walter Kohn, everyone was starting with Hamiltonian, and then Walter was trying to criticize that Hamiltonian is not right. And he decided to go the same path. He just looked on the paper he needed to present, wrote down Hamiltonian on the blackboard, and it didn't fail him, this trick. Everyone was discussing Hamiltonian and he was safe.
On the PC, because right now I don't see any
So-
USB that is open. Like there's a one USB,
In generally,
there's one
the-
flash drive pin.
density functional theory,
Oh yeah.
which is a
There's
protocol
USB in the
to
back here. I'm not
connect
sure if that's USB output.
electron density with total energy, can be formulated without any wave functions or orbitals,
I think
based on
that's
the
the only
theorems.
USB
And
that is-
there is a group of people who are developing so-called orbital free DFT, like very pure, true DFT.
Oh, okay.
And
Okay.
typically it is used for like
Okay.
plasma at high temperatures, high pressures.
Yeah.
But for simple guys like us, for real molecules, we partially violate ideal statement of the DFT. We will be using a little bit of the orbitals concept for assessing the. You may try to turn your microphones off because we are hearing feedback. Maybe because something was changed in the room. We will be using some elements of the orbitals in order to produce kinetic energy. But for all other terms in the total energy, we still will be using the equations based on density only. So here are the two theorems that you recently looked on, right? So first theorem that density gives everything, and second that if you know correct density, you will know the correct energy, and any other density will give you energy bigger than the correct one. So there is a plan of what are we going to do, and we can follow which step we are doing. Finally, if we successfully and if you survive this meeting, we will set up a feedback loop. So we will, in addition to total energy, we will introduce potential somewhere in the middle, and we will introduce orbitals for kinetic energies. But all of them together will allow us to generate density, and then we will cycle it in a loop in the same way as we did for Hartree-Fock theory. Should we try it? Should we try it now?
Yeah.
Can you just set up recording on the remote side,
I cannot do that.
as Daniel typically
No, you
Just-
cannot. You're too sensitive. So just have to record. Oh, maybe it's-
it doesn't want? Okay, so there are well, let's just go forward. We do know the several background theories, including Thomas Fermi's theory, and we do need to take into account attraction between electrons to nuclei, for sure, if you want to describe molecules. And we need to take into account electron-electron interaction. So, a little bit, there is nothing new in this slide, but it is important to go over just to convert our mindset from the language of wave functions and orbitals to the language of densities. So, are you going to object this equation? Just because you don't care, or because it looks so natural for you? So, what is shown here, if you do know the external potential, which is just charge of each ion, position of ion minus position of electron, right? And you multiply it by density of overall electrons and integrate over all space, it will give you total energy of attraction between electrons and nuclei, right? So expectation value of electron to nuclei attraction. Make sense? But on the language of density, it is integral external potential times density. Now, let's do a little thing as we perform when we practice calculus. What if we need to look not on the overall result of integral, but just a little increment to the result? A little differential of the resulting stuff. Then we need just function times differential of whatever is in this, of our integration variable, right? You're following and you're not objecting. Good? And now, should I try once again?
Yeah, it's okay. Like, can you drag the recording screen up to the screen so that I don't interrupt your lecture or something?
Okay, then let's.
Is it okay if you don't record today?
Let's keep it for today.
Okay. Yeah, I'm sorry about that.
Okay.
I just
Yeah.
not sure why it's not.
Okay. So there will be no recording today. Decided. So if now we divide left and right sides of this equation, here I'm showing the same thing with this delta here and delta the differential. Now let's divide left and right sides on this delta rho. So increment of energy contribution to electron to ion attraction is external potential times increment of density. So it's simple writing, but a little crazy abstract thing. Now, let's divide left and right by delta rho. Then division between increment of energy, potential energy, and increment of density will give you external potential. Object if you want or if you can. So it's very straight logic, right? I didn't cheat anywhere. No? But now it looks very crazy. We are taking derivative of energy over density, and density is not a variable, it is a function. So it is a functional derivative.
Yes.
Right? So if you take derivative of energy over density, functional derivative, you will get external potential. So it is a way to extract potential from the energy. We will be using it again and again, and it is nothing super new, but it is really important for the procedure how density function works. And it is one of the very few equations that you may want. Well, I'm not telling memorize, but write down in the Microsoft equation editors and put into your written report. Just look at it and make yourself familiar and make sure that you do not have conflict with this equation. And same as in the calculus, you can see that in the limit of this increment of density is going to zero, infinitesimal. So it's a functional calculus, functional derivative. Instead of usual derivative, you have functional derivative. So here is your old-fashioned, or our old-fashioned way to regain energy out of potential and density. But in some sense, this can be written as V is potential integrated over rho. Now it will be a functional integral. So going back to the total energy. Are there any news?
Oh, it's nothing. Like, this lecture is recorded, so all you have to do is talk to Daniel later and he will send you the lecture.
Oh, okay.
Yeah,
Yeah, it is well.
Yeah.
Thank you. That's good. So, total energy is kinetic energy of electrons, the part of attracting to nucleus, and then electron repulsion, which includes, based on Hartree-Fock theory, two terms: direct Coulomb, exchange, stabilization, and there is one more term that we didn't consider. But there is another form of electron-electron interaction. So, if we live under approximation of independent electrons, then multi-electron function is just product of them. But if we diagonalize multi-electron function, take into account interactions, the mutual positions or mutual shapes of the one electron orbitals for each specific electron will be different. They will be correlated. And Queenie, can you come here and help me?
Sure.
Do you see the chair from the camera? There is a chair here. Okay. I'll put it here. Wait here. You see the chair here, right? Just show your hand if you do. Good. Now, suppose it is like helium nuclei, right? So we together are helium atom. Queenie is the first electron, I'm the second electron. We are both so attracted to the chair, right? And we are electrons, we are repelling. Can we together stay at the same spot? Like if I approach him, can I stay here? No, see, natural. He goes to the other side, right? If he tries to come here, I will also try to escape, right? So what we are doing, we are behaving like two electrons in helium atom. And what, based on one electron theory, each of us should freely walk anywhere we like. But we know that we are not independent. And we are trying to be a little away from each other. So what you saw is called electron correlation. There is a specific term in it. Thank you, Queenie. No, Mary, you are away from the microphone. You need to put it on if you have a question. And in the lowest level theory, like Hartree-Fock, this correlation is absent. But if one goes into wave function theories, next level, it will come up. It is an important correction, and there is no nothing against to include it into density function theory. It should be there, right? So the density of product of first and second electron is not equal. Density of two electrons is not equal to density of product of first and second because of the correlation. And the correlation energy is difference between energy computed in the approximation that Queenie and I can walk anywhere we like, minus energy computed with understanding that we are trying to escape each other. So this difference is called correlation energy. For many years I wanted to change this figure. It should, this line should look this way, opposite direction. So, here. Trying to escape, rather like red if we would attract to each other, and green to repel. Good. Now, all things that we are doing are important. I cannot rank what is most important, but the one that is on the table or whatever on the board is one of the most important things. So there are density functional theories is simple, but each step in it is a little counterintuitive, right? So it's not complicated because of the math, but it is counterintuitive because logic of density functional theory always goes a little out of box. And it's very natural if you feel slight discomfort. So, what is shown here? Do you have any, do you want to give any interpretation? You can put microphone on if you have ideas.
Conservation of energy.
Huh?
Conservation of energy.
Okay, one of the guess was that it is conservation of energy. Conserve energy. Other guesses. Which other ideas you have? We are not hearing you. Still not hearing. We need to learn the language of people with like. You can type SMS to someone in the class and then to pronounce it. Any ideas? What is shown here, other than conservation of energy? So it is a strange equation that includes electron repulsion and electron and nuclear attraction, right? In the real world, we do not have freedom to select what is the energy of electrons attraction to ions and what is the energy of electron repulsion. This is defined for sure for each molecule, right? There is absolutely the only one correct answer. But here we are doing a trick. We are multiplying both of them by a factor. And this factor is changing between 0 and 1. So when this factor lambda is 0, 1 minus lambda is 1. When this lambda is 1, 1 minus lambda is 0, right? So it is like a little bar where we can put the volume in your sound speakers from 0 to maximum. And we can maximize electron to nuclear interaction and then minimize electron to electron repulsion, or otherwise. So here's one of the important counterintuitive things. If we believe that density determines total energy according to the second theorem, the theorems do not tell how we get to this total energy. What is the relative contribution from different parts of the Hamiltonian? What is the relative contribution from electron to nuclear attraction or electron-electron repulsion? You're following, right? So it's theorems do not mandate us to do specific things. On the other hand, electron-electron repulsion is a big pain in the part of the body. If we can avoid it, we should. And because science is done by people for people, why should we torture each other? Right? So here is an idea. I do not know how to type it or verbalize rather than in a discussion session, but please try to focus and get the main idea. We can change relative contributions of electron to nuclear and electron-electron energies in such way so that the total energy will stay constant. Mathematically it's possible, right? So we will modify these factors in front in such way that the total energy will stay constant and we do not violate any theorems. So we will still compute both this energy and this energy out of density, and we will get total energy, well, plus kinetic, in a correct way. So there is a way to get correct energy for wrong relative proportions between attraction to ions and repulsion between electrons. Okay? On other glance, aspect of view, one can say that there is true universe in which we live. So in energy does conserve, but it is a little different thing. It is finding total energy of different contributions. So true universe. When both of these factors have the same proportion, and there is a imaginary, fantastic, unreal, fantastic universe where lambda equals 1 and 1 minus lambda equals 0. So there is a we are allowed to set up lambda equals 1 and lambda 1 minus lambda equals 0 without violation any of the theorems. It will correspond to a fantastic universe where electrons are attracted to ions, but they do not repel each other. So we can still work in this imaginary universe, tweak slightly equations that will connect density to energy, and then tell that this auxiliary universe help us to predict correct energy for the true universe. now you see which steps you need to do if you want Nobel Prize in the future. Think out of the box and do crazy logical steps. What is the price to make such step? If we want to depart from realistic universe, if you want to set factor in front of electron repulsion 0, then the form of converting density into electron to nuclear energy should change. It should be some specific formula that will equivalently replace the electron repulsion. So we repartition total energy function in such a way that we keep total density and keep the same total energy. So here is the total energy in true universe, and here is the total energy in the auxiliary universe. We set up the lambda parameter in front of the electron repulsion 0, and therefore the thing that corresponds to that we were calling external potential when we were in the true universe will be replaced by like potential with factor lambda, right? And it will be different lambda. So we are coming closer to the quantum theory, to the density function theory. The only thing that we didn't resolve yet is kinetic energy. We may want to take care of it in a way that will be most efficient, that will save our effort. This is a standard way how we deal with kinetic energy if you do have orbitals. And it is so, general quantum theory is counterintuitive, but we are dealing with it for so long time that it becomes our second nature, right? It's a really comfortable discovery of using eigenstates of these kinetic energy operators in the language of orbitals. If you do have something efficient and good, we shouldn't throw it away. Let's just keep using orbitals. Although it is slightly against overall theorems and spirit of density function theory, it's just so convenient that we cannot resist using it again and again. So, one more little equation that is absolutely correct mathematically, but slightly counterintuitive. So if total energy is adding together external potential, modified external potential and kinetic energy, then this modified external potential is total energy minus kinetic, right? Simple, you don't object, okay? Just moving terms between left and right parts of equation. And now, the external potential that is functional derivative of the external total energy, or the energy that comes from the term that originally was corresponding to electron to nuclear attraction, is a functional derivative of this delta of V term over delta of rho. Right? Functional derivative of this energy over density, right? But this term corresponding to electronic interactions is nothing but total energy minus kinetic energy. And total energy, we believe that is known. Kinetic energy can be always found if we use orbitals. And now we can tell that external potential, that it is a key unit involved into the theory, can be extracted from total energy and kinetic energy contribution by functional derivative. So here we remove kinetic energy from total energy. Practically, why it is done, why it is more comfortable? Because most of the terms in the total energy look like diagonal, and kinetic energy includes gradients. It refers to neighbors in the space. And if you can remove it, it will be mathematically easier. So this is another, like maybe this form of equation. So V, external potential in the auxiliary world of Kohn and Sham, is functional derivative of total energy minus kinetic over increment of density. We are not yet done. When we will be done, you'll start seeing beauty of this theory, which is so much simpler than wave function direct theory, so much quicker, and it just, as a price for it, we use a couple of counterintuitive steps. So let's focus a little bit on kinetic energy and generally on the algorithm. So we do have a way to write down an equation for external potential, which was a reflection of electron to nuclei attraction in the real world, and in the world of Kohn and Sham it is a little different thing. It includes other interactions as well. This external potential, it is what is coming into Hamiltonian if you would formulate everything on the language of multi-electron wave function. If we give up dft and suddenly we decide to return to wave function, we will have kinetic energy, external potential acting on unknown multi-electron wave function, given total energy and wave function. So we are coming back to the same idea as we started at the beginning of the second chapter of the class, when we just started multi-electronic wave functions and we accepted that there are too many variables that we want to represent to give up wave functions with many independent variables and represent them as products of one wave functions. The mathematical approach for solving multi-electronic equations, for multivariable equations in partial derivatives, is what? Who took differential equations? Okay, who? 1, 2, 3, 4. Okay, separation of variables, right? When separation of variables is possible?
When like each coordinate is represented in its own term. And
Good, good, good. Agree? Good. So if our differential operator has contributions that would correspond to each of independent variables, and we can add them together as summation, right? Then the wave function can be, or whatever, unknown stuff, psi of R1, R2, can be represented as product of theta 1, R1, theta 2, R2, and so forth. So we can write down kinetic energy operator for each electron separately, right? It will be just second derivative over position. Kinetic energy differential operator for each electron will be independent. It will affect only its own variable. So we can split this multi-electron Hamiltonian, which is missing electron-electron interaction, right? So the electrons are not connected. Therefore, we can chop it onto portions that refer only to separate electrons. So it is an ideal situation to set up separation of variables, right? And we did set up this situation by going to the universe of Kohn and Sham, where electrons are not interacting, and we were able to do it because of the second Kohn theorem. Now, if we are going to separation of variables, we need an equation for instead of one big equation for multi-electron function, we are going to set up small equations for one electron functions. And then we will set up their product or whatever, Slater determinant as the answer. So here we put kinetic energy term, which will be gradient over electron 1. And then we notice that since electrons do not interact, the external potential for each electron will have the same functional form. Therefore, each of these little Hamiltonians and each of these sets of solutions for these one electron orbitals will be the same. They are equivalent to each other. So we are performing conversion from multi-electron wave function, right? Kinetic energy, external potential, multi-electron wave function, to Schrödinger equations for one electron orbitals that originate from idea of separating variables. We are allowed to practice the separation of variables because there is no term that will mix R1 and R2, right? The total energy will be summation of energy of all orbitals, and if we add together this little h, we will get our overall Hamiltonian. So, in the same spirit, in the same way as we did at the beginning of the second chapter, we will decide that we can solve this equation, which will be, in some sense, very analogous to Fock equation, right? Equation for molecular orbitals. And then we will set up Slater determinant of all occupied orbitals, and it is not Fock, it is Kohn-Sham orbitals. And their Slater determinant will give you wave function of the system. Note that we are not in the real space. We are not in the real world. we are in the world of this auxiliary universe. And these CHEM orbitals are not actual molecular orbitals. They are computed under assumption that electrons do not interact, which allowed us to separate variables. So it's still an abstract construction, but it is very appetizing and useful construction that later will bring us to the correct total density. Are we happy by now? No, we are not happy. No, we are not happy. Why we are not happy? It looks like everything is great. We can find wave function, and if you know wave function, we can find total energy, and everything is great. Theorems just helped us to reproduce another approximation similar to Hartree-Fock theory. No, it's not the whole story, because we didn't connect it to density. Like, if we want to refine it, we still need to extract density out of this wave function, and then feed it into expression for the only thing that we can vary here. So we need to connect this multi-electron wave function to total density and plug this total energy into expression for external potential. If we do it, we will be set up to start programming or to hire a professional programmer to write another DFT code for us. By the way, it is possible. One of the recently defended grad students from physics, from the same group as Nathan, wrote a DFT code on his own because he was bored. Just for learning purposes. And it was working. Maybe not as efficient as commercial codes, but it's possible. It's not something super complicated. So get total density out of this expression. Okay, I sign. I agree. Build total density out of one electron orbitals. So I'm going to go over little practice, a little equations that is possible to derive. Again, you just sit, relax, lean back, and sleep. But I'm going to show very trivial thing that how to get total density out of Slater determinant. And we cannot, well, I do not have steam to do it for like 3, 4, or 100 electrons. We will do it just for 2. And you will be positively surprised by the answer. So if you elect to sleep and relax, I will declare the answer, so that you do not worry. And the answer is very trivial, it's very natural. So the total density for the system of n electrons, here it will be 2 electrons, is summation of density for electron in orbital 1 and density of electron in orbital 2. So summation of densities for all occupied orbitals. Okay? This sounds very natural and very simple on the first glance, but on a second glance, if we would live before Kohn derived his theory, or before he was got the prize and everyone started to believe that it is the right theory, it looks a little strange. Multi-electron wave function is substantially multidimensional object. Density will give us total energy of this multi-object. How can it be so simple? Is there any cheating? Is there a proof that it is so? So we are dealing with Slater determinants, which are anti-symmetrized. Should it be some anti-symmetrized terms in the total density? It's like too simple to believe. So what I'm going to do, I'm building. So I do have two set of Kohn-Sham orbitals. To follow the book of Irvine, Levin, I will assign the letters, instead of phi, it will be theta for orbitals. So 1 electron Kohn-Sham orbitals. Here, there are only two orbitals in this consideration, first and second, two independent positions, R1, R2, and we do believe in Slater. Well, in Slater determinant as a fundamental concept for antisymmetry of multi-electronic wave functions, to be precise. So if you have two orbitals occupied by two electrons, it will be orbital 1, electron 1 in orbital 1, electron 2 in orbital 2, minus electron 1 in orbital 2, electron 2 in orbital 1, right? With minus. If we do want to practice total density or total probability, no one canceled the definition that absolute value of wave function square will give probability or density. If it is multi-electron wave function, then our probability of R1, R2, or if you are on the language of density, rho of R1, R2 will be wave function of R1, R2 star times wave function of R1, R2 without star, right? Is a typical way how we do it in quantum mechanics. No objections. Therefore, we need both wave function and its conjugate. So when we do conjugate, everything stays the same. We just write a little star on the top of each theta orbital. Good? There is a little, I wouldn't say trick, standard approach. What if we do have this density that depends on two variables, R1 and R2? And by all spirit of density functional theory, we need density as function of one variable, right? We measure, or we think about number of electrons, or density of electrons per unit, per infinitesimal volume, right? All electrons. We do not need many variables. We look only one variable. And here we have two. How do we get rid of second variable? We just integrate over it, right? Make summation. So we put integral, and we integrate over R2, right? So we need a wave function conjugated, psi star, wave function without conjugate, and then integral over R2, which is not visible here. Make sense? Now, I do have a special favorite question of Mary. Prepare. Concentrate. Everyone, it's a favorite question of everyone. Drink coffee and prepare. So, we are going to practice a product of two factors. This factor and this factor. Each factor contains two terms. First term, second term, third, first. How many terms will be in this result of this product? You can show it. 4, yes, correct, right? So this, it will be first term. Second will be this, and this. Third will be this, and this. And fourth one will be that, and that. Correct? Okay, you save me time, I will not write it down. There should be slides. Yes. Okay. I already have it pre-made. So, 4 terms. 1, 2, 3, 4. First term has sign plus. Last term has sign plus because of cancellation of 2 minuses. And 2 terms in between have minuses. By now, this is our total density, right? You see, it looks ugly, as it should be for multi-electron things. Good. No one has doubts if things are ugly. It will be more surprised if it will convolute to something simple. Now, if you would do it carefully, which probably will skip. So first, second, and then first, second. So and star, no star. First term is clear. And in the next terms, we do have mixing. First, second, and here first electron in second electron in first. We are integrating it over R2, right? So I'm bringing your attention to the right, yellow, to this second line. So we're integrating over R2. We have 2 things that depend on R2. Theta 1 of R2 and theta 2 of R2 is star. We believe that the world is set up in a comfortable way for us, that wave functions are always orthogonal. If they are orthogonal, if these orbitals are orthogonal, what will be the integral of the orbital 1, orbital 2 over their integration variable? You can show with fingers. Any other opinions? So the indices here, 1 and 2 are different, and orbitals are orthogonal. If you integrate product of non-equal orbitals, which are orthogonal by definition, yes. Well, from second attempt you were right. 0, right? Because of the orthogonality. What does it mean? It means that we can cross out the second line, right? What if you look on the third line? The variable R2 comes once here and once there. Once for theta 2, once for theta 1. Again, due to orthogonality, integral of this stuff and this stuff over that stuff will be 0, right? So we cross out the third line as well. What is going on in the first and last lines? Yes, correct. So here we have 2 things that depend on R2. Theta 2 of R2 and theta 2 of R2. And the integration will give you 1 because of orthogonality. And the result will be, the integral will be removed and you have only theta 1 and theta 1 of R1. Okay? Now let's look on the last line. What does depend on R2? Be careful. Again, it comes twice, and here it comes as an argument of wave function 1. Right? So theta 1 of R2 and theta 1 of dr2 will give you 1. So the only thing that was not cancelled or multiplied by 1 is here. Theta 1 in the point R1 squared. And here, look carefully. theta 2 into point r1 square, right? So just by mechanics, how the world is organized, we didn't tweak anything. We literally practiced Slater determinant. But it came that we are arriving to orbital 1 of at the point r1 squared plus orbital 2 at the point r1 squared. And we do have factor 1/2 because of the Slater determinant. Remember this 1 over square root of 2, right? So it is a little discovery that makes our life so easy. So even if we do know multi-electron wave function, which is anti-symmetrized with Slater determinant, total density will be just summation of all occupied orbitals squared. This is a really great thing. This makes all life as a like entertaining park. Good. And if you have more than 2, it will be just plus 3rd orbital, 4th orbital, right? So how do we interpret where we are? What do we have now? We have a procedure to create density out of wave function, right? So we do have total density. Now, if you do have total density, we can plug it into the expression for the functional derivative and get external potential. And if you have external potential, we can plug it into Kohn-Sham equation and get orbitals. And then we can take orbitals and construct total density. And repeat. Did I introduce in this audience a joke about programmer in the bathtub? I did? Mary doesn't remember it. You don't? Okay, I'll take a pleasure. It's so much easier than speaking about equations. So a company hired a programmer, and he was working well, doing all assignments. Suddenly he didn't came to the work. So the company sent a team to check if he is okay after a couple of days. So they came and found him alive, but blue, cold, laying in a bathtub, holding a shampoo bottle, reading, apply to hairs, rinse, and repeat. So it is what we are going to do is density functional theory. So compute total density, plug into expression for functional derivative, find external potential, find orbitals, find density, and repeat. Okay? Okay, it is the same thing, just with a little better font. For terms, terms with minus sign are cancelled. Terms with positive sign are left. So it is one more equation that you please plan to, well, we are adults, we do not need to memorize anything, but please make yourself comfortable with this equation and prepare to copy paste or type in this equation editor or LaTeX, whatever you're using, for your written reports. So written reports will mimic true research papers which have methodology section. If you will select to do your written reports based on DFT, which is not mandated but highly recommended, this is one of the equations that explains how DFT works. So as soon as you find orbitals, you add together, adding together orbital squared over I goes from 1 to number of electrons, all occupied orbitals, of R, and it will be a total density. Then this total density, this is blocked, I will rewrite it. This total density will go into equals delta rho of E total minus E kinetic, or whatever, letter T, kinetic energy. So this total density determines total energy, right? And kinetic energy can be found just by applying gradient, second order derivative, right, for the orbitals. And when you subtract total energy and kinetic energy and apply functional derivative, you will get the external potential, right? And then this external potential will enter CHEM. No, it's not end yet. No, do not believe it. So, rho equals summation theta I of R absolute value square, number of electrons. The V as functional of rho is d rho total energy as functional of rho minus kinetic energy. And then this, so it becomes whatever, here, there, and then kinetic energy plus external potential that depends on density applied to unknown orbital gives orbital. And now we do practice that orbitals obtained from the CHEM equation are fed back into definition of density. Sub I. Okay, so by now we are not going to do it today, but by now you are ready to program a code for density functional theory. You set up a self-consistent loop until total energy will converge to a value smaller than R, right? So from orbitals you get density, from density you get, through this functional derivative, you get external potential, from external potential you get CHEM equation and you get orbitals. You have a closed loop. Of course, we are missing explicit expression for total energy. And this is the major challenge in the field. But independent of whether we do or do not have this expression, theory does work and it is proved to be correct. So through generations of scientists, there are ways to improve this expression, how to express total energy as functional of density. Just as a little glance forward, it should be looking similar to what we've got in Thomas Fermi theory, right? So like total density in the power, whatever, 5/3 integrated over all space. Or maybe something a little more advanced, but not very complicated. Equation that practices functional of total energy out of density. Minus kinetic functional derivative, which is also possible in practice. So we are going through these equations more for educational purposes, right? In practice, this step of expressing total energy and taking functional derivative and getting external potential is unified. In fact, there are analytical expressions for functional derivative that one practices immediately after getting density. Okay? And then it goes into here. What is partial charge files that you are getting in VASP? those are not when you plotted them. You saw that when you plot them in like Gauss view, they do not change color as Fock orbitals change, right? Because it is densities. So it is theta squared, right? They're always positive. Just the WASP software is designed such way that it doesn't want to store and give users orbitals. It gives immediately density, because summation of density is something really needed for GFT. Good. Done. Thanks much for investing your time. I didn't announce your entertainment for the weekend. I'll design something, but the due date will be later. So you are recommended to start earlier, but do not worry. There will be. I definitely will not be able to come to class on Tuesday and arrange any grading, even if you are continuing doing the grading. Highly likely, the homework will include making heating and molecular dynamics for another model, and preparing movie, uploading it to YouTube and sending link to instructor. By now, there is one person in the class who successfully did it. So it's Kurt. So he will be your guru if you do not hear any instructions from me. Done. Have a nice weekend, and see you in a week from now, next Thursday. While the classes will be still here, and someone will come when